All right, so now let's try doing another type of double integral. Right? So here we're asking to integrate z equals 5 over the region bounded by x equals 0, y equals 0, and x plus y equals 1. All right, so what I really want to emphasize whenever you do one of these, and this should always be the first step, right? I really want to emphasize this. Sketch the region you're integrating over. Always do this. Unless you're at a point where you can immediately just see exactly what's going on, always sketch the region. Okay? Hopefully I made that clear enough. Always sketch the region of integration. Okay, so let's go on to sketching the region of integration. Right? So what does this thing look like? Well, it's a pretty simple little region. X equals 0 is the y-axis, y equals 0 is the x-axis, and this line, x plus y equals 1, well, it's this line right here, this diagonal line. Right, so we also have this one and this one. So this region we're integrating over is this triangle inside here. Right? And let's label these edges. This is x equals 0, this one is y equals 0, and this one is x plus y equals 1. All right, so you might notice something new here. We're no longer integrating over a rectangle, but now we have this triangle-shaped thing. Right, well, it's actually exactly a triangle. It's not just a triangle-shaped thing. It's a triangle. So how do we integrate 5 over this region? Well, let's think first, what does this region look like? This solid, right? Since 5 is positive, we can see it as the volume. Underneath z equals 5, that's just a plane, and above this triangle. So that's just a triangular prism. So we know, just from doing geometry, that the answer should be, well, it's the area of one of these triangular prisms is area of the base times the height. So the area of the base is 1/2 base times height. Then our base, yeah, the height shows up twice here. So area of the triangle is 1/2, 1 times 1, then times the height of the prism. So we should just get 5/2. Right? We can see that from basic geometry. All right, so how do we actually set up a double integral to give us the volume? Right? So we want to integrate 5 in some order that will give us 5/2. All right, so remember when we're integrating over a rectangle, if we integrate y first, that means we go from the bottom to the top. If we integrate x first, we go from left to right. But there is another little trick. If you remember inside the Riemann sums, when we did the first integral, we had to fix one of those sample values for y, do the x integral, then we integrated with respect to y. So we have to take what are called sort of slices of this domain. So let's say we decide to do the y integral first. All right? So that means first we should be integrating from bottom to top. All right? So we have to fix one of these arbitrary x values. Let's say we pick that one right there. All right? Probably shouldn't have scribbled in this triangle here. Let's go ahead and clean that up. Okay? So let's say we fix that little x value there. All right? And then what we integrate over in this first one is this slice right here. Right? So we fix some x value, an arbitrary one, and then we integrate over this. Right? And what will that do? That actually tells us the length of that little segment there. All right? So how do we set up the bounds? Well, the bottom one's pretty easy. Y is always 0 down here. All right? But at the top, now it really depends on where that x value is. Y will change with respect to that x value. So how do we incorporate that? Well, here we have an equation for that line. We can solve it for y, and it's y equals 1 minus x. So now we have an interpretation of the height of this with respect to the fixed x value. So that means the upper part of this integral is just 1 minus x. Right? Hopefully that makes sense. So we're still doing the same kind of thing we did for the rectangles, bottom to top, except now, well, the bottom here is still a line, but the top is a slanted line. But we can still describe it as y equals some function of x. All right? So this is still the top. All right? And then for x, which has to come next, well, in this case, all we have to do now is just add up over the range of x values. All right? So there should be no variables here. All right? And in this case, we just get 0 to 1. Right? Because x can go all the way from 0 to 1. So, why is there no variable here? Well, remember what we're doing. This first integral gives you the length of that pink line. Right? The next integral, what it's really doing is it's adding up all these little lines here to give you the area here. Right? That's sort of intuitively what's happening. All right? Or if you want to think of it more geometrically for the integral itself, doing this first integral is giving you the area of the little slice of the triangular prism. And then the second integral, the dx integral, is stacking all those little slices next to each other to make up the prism, and then the integral binds all those together and gives you a volume. Okay? So let's also set this up where we do the x integral first. All right? So it'll still be 5. But now we want to do dx dy. All right? So it's basically the same idea. Except this time, what we do is we fix some y value and look at a slice this way. Right? So, and now x, remember x goes from left to right. So, that means our bounds for x, the leftmost thing is 0. The rightmost thing is this line. And this line, now we have to solve it for x. And it's just 1 minus y, right? So that means the top bound for x, which is the rightmost part here, is 1 minus y, right? Okay, and then we do the same thing as before. Now we just add up over the range of y values, and y starts at 0 and ranges all the way up to 1, all right? So we'll just summarize real quick, and then we'll compute this integral. I just want to summarize that integrating, so x goes left to right, y goes bottom to top. Right? And that's the philosophy for setting up the bounds in terms of x and y. Right? And another little comment is the outside integral here, no matter what the region is, should never, ever, ever, ever have a variable in it. This outside integral should only have numbers. Right? And this inside integral, right, either of the bounds should never have the same variable you just integrated with respect to, right? So for example, in the second one here, neither this bound down here or this bound up here should have an x in it. It doesn't matter what the region is, it should never ever have an x. If you integrate x first, there should never be an x. All right? Hopefully that makes sense. Okay, so now let's finish computing this. All right. So when we compute this, it's pretty much exactly what we did before with the rectangle, except now there's a function. But no big deal. Right? So 0 to 1. Integrate 5 with respect to x, that's just 5x, from 0 to 1 minus y. All right? So that's just integral from 0 to 1 of 5 times 1 minus y. So that's 5 minus 5y minus plug in 0. Right? So this is just the integral from 0 to 1 of 5 minus 5y dy. Right? Now when we integrate that, this is just like Calc 1, 5y minus 5 halves y squared from 0 to 1. So here we get 5 minus 5 halves minus, well, 0 minus 0. So then just 5 minus 5 halves, which is, of course, 5 halves. And that agrees with the geometric computation we did. All right? So that's basically all there is to doing double integrals over more general regions. All right? It's just kind of break your region up and see, is it easier to describe as left to right or bottom to top first? But you also have to weigh that with the function you're integrating. All right? So let's do some more examples, and hopefully it shouldn't be too bad. All right? But remember, step 1. What is step 1? Step 1 is always, 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 always sketch the region of integration. All right? If you do that, you have a so much smaller chance of making a mistake on your bounds. It'll really save you. All right? So remember, sketch your regions.